All right, so we construct the graph of the log base 2 function by the 2 to the x function, and then reverse the columns, graph both. Here it is. We want to estimate log base 2 of 3. What do? Well, log base 2 of x function, 3 is now x, so we're going to go to 3. And then we project up and over, okay? Now, this is kind of a badly drawn graph, and I've got a little dip in it. The graph is concave down. If it was a straight line between here and here, because the value here is 1 and the value over here is 2, if it was a straight line, you would expect the value at 3 to be halfway between 1 and 2, which would be 1.5. Since it's concave down, it's going to be a little bit above a straight line, so probably a little higher, a little more than halfway. Halfway is 1.5. A little more than halfway, I wouldn't go much beyond 1.6, okay? So, according to my graph, which has a little bit of a dip in it, unfortunately, just between the board and my arm, it looks like it projects pretty close to 1.5, so that's what I'm going to use. But I know that it's a little bigger, okay? So let's see here, 1.6. Would have been better. Okay? Okay, well now, let's find 2 to the x for this value, right? Okay? What's that mean? Well, by this value, I mean this value, the value that we just done got. Okay? Well, okay, here's 1, here's 2, here's 1.5. We project up here. And it looks like, according to this badly drawn graph, we get 2, right? Well, we know that really at 1 we should have had 2, so really this graph should have been a bit higher here and probably a bit higher here, so maybe the graph should have been like this. Okay, so now maybe when I go to 1.5, I get something about here. Okay, so correcting my 2 to the x graph to fit the scale that's correct with this, what do I get? What's this look like?
3.
Because here's 1.5, right? So this looks like what?
3.
It looks pretty close to 3, doesn't it? Okay? The estimate is about 3. Now, should that be? Well, if 2.5, I'm sorry, if 3 gave you a value of, can't write anything without screwing it up. Okay, if 3 gave you a value of 1.5, then what would you expect to see on this table?
1.5 gave you value.
You'd expect to see the values reversed. Well, 1.5 would then go in the first column, that would be here, and it would give you 3, right? Now, if you do an honest estimate with a better drawn graph, more accurate, okay, it's not going to work out perfectly, okay? And matter of fact, I'll tell you for sure it isn't perfect. Okay, now, one great thing about logarithmic and exponential functions is sometimes you get to use your calculator, okay? That's related to the fact that, like, you can't calculate on paper what 2 to the 1/2 power is. We don't include it in the graph for a reason, and that reason should make sense to you, okay? The sense being that not sure how to put it. But sense simply being that the reason we don't include it is because it can't calculate it. Therefore, if you want to get the value, you'd better have a calculator, okay? There's no more efficient way, and it's perfectly appropriate if you need an accurate value to check your estimates. That doesn't mean when I say estimate it, you go to your calculator, punch it in, and write down a 6 decimal point or a significant figure result from your calculator. That's not an estimate, and I penalize that when I ask for estimates. I penalized it a little bit, didn't have too many of those, but I penalized it a little bit on the major quiz. I'm going to penalize it much more heavily next week. When I say estimate, you don't go to your calculator because that doesn't reinforce these relationships. That's just numbers that come out of the ozone. Unless you understand these relationships, then you can understand the calculator does something. You know, they have better graphs than you do, so they can project more accurately, right? You know, all kinds of graphs in your calculator. And they know how to rescale. Actually, they use Taylor expansions, but you won't know about that unless you take a good calculus course next year, 2 semesters. Okay?